this is the second lecture of this module, control volume analysis of systems, correct? So welcome back to this session. So this is the second lecture. So in this lecture, we are going to look at one very important, good evening, of course. Good evening, you and Shrikant. So in this lecture, we are going to look at this Reynolds Transport Theorem. And also we are going to see the deductions. Means basically once you have this theorem, you have something called corollaries, correct? You will actually derive some, or basically you will deduct some results from the theorem. So similarly here we have the Reynolds Transport Theorem, which is one of the very fundamental and of course very important theorem actually, if you see. Okay, so now this is the Reynolds Transport Theorem, and from this we are going to deduct this linear momentum equation and also the angular momentum equation in today's session. Clear? So that has to be understood clearly. And before going straight away, we will give you slight revision of what we have learnt in the first lecture. So I told you many times it's not possible for you, like for example, if you have a flow, then in differential analysis what we have taken some small element in the flow and we try to analyze the things. Okay, but sometimes you have to actually take the complete volume to understand what's happening in the case. Okay, so we in yesterday's class we have defined control volume. We defined what is a control volume, correct? So we defined a control volume. So control volume is basically that volume which is under study, okay, or the region in space which is under study. And I told you control volumes can be stationary or they can be movable, sometimes they can be deformable also, for example. Okay, so now if you see this, we have defined what is a control volume. So we have seen this is region in space that is under study. Region in space which is under study. Okay, so this is the region in space which is under study. So now from here we have identified what is this Newton's third law of motion very creatively. So we understood this Newton's third law of motion, correct? We have seen this Newton's third law of motion, which is actually important in this particular understanding of the subject. So we defined what is Newton's third law of motion. So we told Newton's third law of motion is valid only when there is physical contact between the bodies, correct? Yes or no? When they are separated, when there is a traveling of the bodies and all, it's not valid. Whenever they are in contact to each other, then only there is certain action reaction force pair which exists between the bodies actually, correct? We have talked about this, and also we have also seen the mass conservation equation which is given by the mass conservation equation which is given by dou rho by dou t plus divergence of rho v bar is actually equal to 0. Correct? This is what we have seen. So these are the main prime things that we have applied in yesterday's session. Of course, we have seen this continuity equation long back in differential analysis also, but we have talked about the continuity equation here in terms of this Gauss divergence theorem, or basically in integral analysis actually, correct? So these are the things that I have defined you basically, or at most in yesterday's lecture in the part 1, correct? So can you all recollect these things? So please type in the chat box. If you are clear with these points, then we will go for the next topic. So please type in the chat box. Yes, correct? Now let us see here. Okay, so this is clear to you. Now let me define you two important things actually. So control volume I have already defined you. Control volume is the region in space which is under study. Now if you talk about system, okay, so system is basically, you will come to know about these things in thermodynamics, but I'm just giving you some introduction. Okay, so system, which is generally referred as the closed system. So this is quantity of matter which is under study. Quantity of matter which is under study. Quantity of matter which is under study. These two need not be same. Sometimes what can happen, from a given volume, mass can flow out of the volume actually. Okay, so system is those number of particles. Let us suppose if there is a class, for example. Okay, so in a class there are 50 students, for example. Let us suppose if there is a particular class for academic year, there are 50 students. These 50 students I am considering as my system. Understood? So those are the particles. So classroom may change, means depending upon the subject they may be shifted from one class to another class, but my system remains same. Okay, similarly let us suppose if I select a room in a college, for example, say in some building, some room I have selected, that room is the control volume. So system can go into the control volume, it can move out. Similarly, whenever you are taking any tanks or something as the volume, then if you store some fluid, sometimes fluid can go out of the system or sometimes it can stay within. Okay, so system is those set of identified particles that are present in the that are presented. Okay, so now this Reynolds transport theorem is actually one very important understanding. Okay, so let us see what is this Reynolds transport theorem and what is the main use of this Reynolds transport theorem. So let us try to identify. Okay, so this Reynolds transport theorem basically connects rate of change of property, rate of change of quantity or property, generally any quantity you can say, rate of change of quantity of a system to rate of change of quantity of a control volume, rate of change of quantity, rate of change of quantity of a control volume, of a control volume, actually of a control volume. So let us try to understand. Look, let me explain you what is the system control volume in a clear sense, then we will go for the much better understanding. Okay, so like yesterday's case, let me take one plate for example. Okay, so let us suppose there is one plate for example. Okay, so this is a plate. Let us suppose if I am thickening this for example, so let us suppose this is a plate that is existing here. Okay, now let us suppose there is some fluid jet which is coming for example. This fluid jet is coming and hitting this. Okay, so this fluid jet is coming and hitting this plate. Now if I take a volume which is here, there is some momentum change. Let us suppose this is the volume which I am interested in. Okay, so let us suppose I want to study something within this volume. Okay, so let us suppose I want to study some change of quantity within this volume that's actually present. Okay, so here if you see, this is your control volume, correct? So let us suppose at any time if I take this is the control volume, so at time t. Now my focus is on the mass of the fluid which is in this volume at this particular time. Understood? So what happens, let us suppose if my fluid jet is coming and hitting this plate in this direction, then at that particular time if I select this is the volume, then within this volume there is some fluid which is present. So I identified those fluid particles and I am telling you that this is my system, means the mass which is in this volume at time t is my system. Okay, so my focus is on that mass as well as this control volume. Okay, so this control volume at time t, or since my system, my mass is within this volume, so I can also call this system at time t, system at time t. Okay, so system is those particles which are in this volume when time is t, at one instant. Now what happens when the flow happens in a small time dt, in a small time dt for example, see what happens in a small time dt for example. So let us suppose you have taken some small time interval dt, then what happens, because of the flow that exists, what happens, my system which is actually like this initially, now my system will take some other form which is basically like this. So there will be some flow which is perpendicular to in this direction, so fluid comes like this and impacts into two halves actually. So that's why let us suppose my system now at time t plus delta t is something like this. Now so this is my system at time t. So this is system at time t plus dt. But my control volume at t plus dt is the same orange dotted line, correct? Because my volume doesn't change. Volume, but of course here in this case I am fixing my volume, so definitely my volume remained the same because this plate is fixed. But my system, the mass which is initially within this orange box at time t, now because of the flow, what happens, this mass will try to move closer to the plate and some part of the mass may go out of this control volume also because they can be flow, correct? So did you all understand how to identify system and how to identify the control volume? Because this is a bit important here. So are you all clear till this understanding that this I'm calling as system at time t plus dt, this I'm calling my control volume. Since my plate is fixed, my control volume is fixed, means at time equal to t or maybe at time equal to t plus dt, my control volume is at the same location. So can I say this? Yes or no? So please type in the chat box. Is this clear to you? System is the quantity of matter which you are studying. Okay, so at time t, whenever this system is within this orange box, now what happens in a small time dt, because of the flow that is taking place, my system, my fluid particles which I have identified, they will move close to the plate and some part of the fluid will actually come out of this control volume as well because of the flow. Correct? Now this is the control volume at time t, or it can also be called system at time t because both are same initially. Now because of the flow, what that's happening, the system actually occupies some new position. Okay, now let us see the general case, the most general case. Look, let us suppose you have a flow, for example. Okay, so let us suppose you have some flow like this, some flow in some direction. It's a three-dimensional flow, whatever you can say. So let us suppose there is some flow. Okay, now whenever there is some flow that's happening here, so see here, this is some flow that's happening in a three-dimensional space. Normally there is some flow. Now let us suppose if I identify some control volume in this flow. Okay, so let us suppose I identified some control volume in this flow, and the fluid which is within this volume, it can be of any shape, some random shape. I have just taken some random shape here. Okay, I have just taken some oval kind of shape or something, so it can be of any shape generally. So this is my control volume initially what I have chosen, for example, let us suppose. Okay, now when I choose this control volume, the fluid which is within this control volume is also my system at time t. Correct? So if you see, this is my control volume at time t. Let us write completely. So CV is what we write generally. So control volume at time t, and also this is my system at time t. Correct? Both are my control volume and system. Now because of the flow, what happens in a small time dt, in a small time dt, now what happens is this amount of system or this amount of matter which is in this volume now try to move slightly. Now if I try to identify my system, let us suppose my system has changed its position because there is some flow. So let us suppose my system got to some new location. Okay, so the quantity of matter which is within this fluid, within this volume, now has, within the small time dt, since there is flow, whatever is the mass in this orange volume initially, that mass might have moved along the flow to some extent. Okay, so now this is called your system at time t plus dt. Means basically if you take this volume, some part of the mass is actually leaving the control volume. Obviously it happens because when you fix a volume, then when there is flows within the small time dt, initially if this fluid which is within this orange volume is taken as system, then within some time some part of the fluid will leave this and some new fluid will actually enter. But this new fluid which is coming is not my system, correct? Because system is the fixed amount of matter which you are focusing on. So this amount of fluid which is in this yellow circle now is my system. That's my system at t plus dt. Now your idea is to calculate what is the rate of change of any property within this control volume. Okay, so now let us see, let us suppose if B is the quantity considered, okay, quantity considered of control volume, for example. Okay, any property B is quantity considered, maybe like mass, momentum, whatever you see. So beta is quantity per unit mass. Quantity per unit mass is what you have here. Okay, so quantity per unit mass. Okay, so this is quantity per unit mass, which means basically beta value is capital B by M. Like normally in thermodynamics and all, generally specific properties. So this is some specific property. Okay, like specific volume, specific internal energy, how you do the things. Similarly here, this is beta is some quantity per unit mass. Okay, that quantity can be like anything, mass of the system, mass of the control volume, or momentum of the control volume, what can be. Okay, now if you see rate of change of quantity of a system, rate of change of quantity of system is equal to dB by dt of system, correct? So this is dB by dt of the system. Now let us try to identify how this is connected to the rate of change of quantity within the control volume. Okay, so let us focus our attention on this. So now if you see, if you want, considering rate of change of quantity of control volume, rate of change of quantity of control volume So this we are considering. Now rate of change of this control volume can be written as dB by dt of control volume. This can be written as, there is something called first principle of differentiation in mathematics. You know this. If there is some function f of x, let us suppose if you want to calculate the differentiation of this, you will calculate the differentiation using limit h tends to 0, f of x plus h minus f of x divided by h. Actually, have you seen this anywhere? So please type in the chat box, have you seen this? Normally if you want to calculate differentiation of any function, then this is called the first principle of differentiation, and using this limit you can calculate the derivative of any function which is differentiable actually. Okay, so we know, correct? This is some common basic idea. So now if you apply this here, we want the rate of change of this property b. So if you apply here, so see here, this quantity is equal to limit dt tends to 0. So let us suppose that small time is actually dt, so or delta t, let us write limit delta t tends to 0, property of the control volume at time t plus delta t minus property of the control volume at time t divided by delta t, correct? We can write this divided with delta t is what you can write basically here. Yes, because as per the first principle of differentiation, within a small time delta t, if the property is changing, then the rate of change of the property within that small time interval is nothing but change of the property that's taking place in this small time interval, correct? Now let us try to identify this. So see here, let us try to identify certain terms here in this case. Now if you see, property of the control volume at time t is nothing but property of the system at time t, correct? Yes or no? Because we know this property of this control volume at time t is nothing but the quantity of the system at time t, because at time t initially my control volume and system both are t. So whatever is the, for example, if I am talking about mass, let us suppose whatever is the mass in this control volume, same is the mass of my system also, because my system and my control volume are coinciding at time t, correct? So if you see this, B control volume at time t is equal to B of the system at time t, correct? Now coming to B of the control volume at time t plus dt or delta t, let us say. Okay, so let us suppose if you identify this quantity. Now what is this quantity? Let us try to understand this. Okay, so now this quantity is equal to control volume at time t is, see carefully here, if I split this for example into first part, second part of the volume, and this is third part of the volume which is actually going. Now my control volume at time t plus dt is only this, means basically if you see control volume at time t plus dt, if you see, means the quantity of the control volume at time t plus dt is nothing but only this quantity of the mass is present inside this, or this quantity of the this quantity is only present within the same control volume, rest has already left, correct? At time t plus dt, my system, means if you see, we have considered a rate of change of system, right? Rate of change of system, correct? Just a minute guys, rate of change of control volume you have considered. Okay, this is the case. Okay, so instead of writing this, let us try to understand one thing. So let us see basically here, control volume at time t, this is the system, correct? So this is system and this is the control volume, so dB by dt of the system. Okay, fine. So if you are considering dB by dt of the control volume, this is what you have. Okay, so first of all let us try to convert. So this is what you have. Now let us again write this dB by dt of the system. Therefore dB by dt of the system is equal to limit delta t tends to 0 b of the system at time t plus dt or delta t minus b of the system at time t divided with delta t. Correct? This is we can write. This is what we can write. Now you know that b system at time t is same as b control volume at time t. Now b of the system at time t plus dt, for example, let us start writing from this t plus dt. So now if you want to know the quantity of the system at time t plus dt, at time t plus dt the system moved from this location to this particular location. Correct? So initially orange circle is the this volume, orange volume is the volume of the system. Now within some small time delta t, because of the flow, this system traveled to this particular location. Okay, now whenever this system traveled to this particular location at time delta t plus delta t, the system is basically in this region 2 plus this region 3 actually. Correct? So this can be written as b2 plus b3 is what we can write. Correct? Because whatever is the system that is present in these two regions 2 and 3 is the system that is available at time t plus dt. Now this b2 can be written as this total control volume minus this sub 1. If you subtract, means if you take this total b1, sorry, if you take this total b1 plus b2 and if you subtract b1, then you will get this. Means you can write this b2 as, you can write this b2 as basically b of this system, b of this system actually here. Correct? So if you see this system at time t can be written as b2 plus b3, so that can be written as b control volume at time t plus delta t or dt minus b1 plus b3. Correct? Because you see control volume at time t plus dt is still this one, because you see this is the control volume which is fixed. So at time t plus dt, if you want the property of the thing which is in this region, you can write that as property of the thing in this complete control volume minus the first part. Correct? So you can write this as b2 can be written as, means the quantity present in the second region can be written as the total quantity present in the control volume at time t plus delta t minus this b1. Correct? So can I write this? So please type in the chat box, can I write this relation? Yes or no? Can I write this? System at time t plus dt can be written as b2 plus b3. This b2 can be written as total control volume at time t plus delta t minus b1. So this gives me b2 plus b3 as it is. So can I write this? So please tell me, can I write this expression? What I have written is basically this b system at time t plus dt is nothing but this at time t plus delta t. This is the volume of the, this is the matter or this is the quantity which is actually present in this cycle. Okay, so here this total quantity I have written as b2 plus b3, and this b2 I have written as total control volume at time t plus delta t minus this first part I have taken off. Correct? Yes or no? b2 can be written as, b2 can be written as b of the control volume at time t plus delta t or dt t plus delta t minus b1. This is what I have written actually. Correct? So what I'm telling you is, yeah, this b system at time t plus dt can be written with this relation. This is what I'm telling you. So is this clear so far? So please type in the chat box. Is these two steps clear to you? If you are clear with these two things, then we will go for the different this substitutions. Now let us continue. So if you replace it here, this implies db by dt of the system is equal to limit delta t tends to 0, limit delta t tends to 0, b system at time t plus delta t can be replaced with this value, b control volume at time t plus delta t minus b1 plus b3 minus b system at t is same as b control volume at time t, so divided by delta t actually. Okay, so this divided with delta t. Now let us split this into two limits actually. So if you split this into two limits, this implies db by dt of the system is equal to, this I can split into two limits, like limit delta t tends to 0, limit delta t tends to 0, b control volume at time t plus delta t minus B control volume at time t divided with delta t. Okay, so this divided with delta t plus limit delta t tends to 0. Now you have B3 minus B1. You have B3 minus this B1. So B3 minus B1 by delta t, correct? So you have this expression B3 minus B1 by delta t. Now you can see this as for the first principle of differentiation. You have this here. So here if you see, considering the weights using first principle, this limit can be replaced with this dB by dt of the control volume. So this limit can be written as, this implies dB by dt of the system is equal to dB by dt, or generally you can write this as, because sometimes what happens, depending on not only with time, the control volume conditions can change with respect to many other things like temperatures, or sometimes depending upon the any environments. In case of gases and all, this is the general theorem that I am deriving. So here if you see, this quantity which is here can be written as partial derivative. Instead of exact derivative, let us write it partial derivative. Why I am writing it as partial derivative is, sometimes what happens, let us suppose you keep some momentum of the gas or something in the system, then when temperature is increased or something is increased, even though there is no mass flow, the conditions in the control volume can change sometimes. Okay, so it not only depends with time, it depends on many other things actually. So that's why we are writing this as partial derivative, dou by dou t of B of the control volume actually. Okay, so dou by dou t of B of the control volume plus limit delta t tends to 0 B3 minus B1 by delta t. Okay, we will see what is this quantity, but before seeing this quantity, look, I want to write certain things here. Property of the control volume, B, or quantity of the control volume, this can be written as, look, we have taken property for small unit mass as beta. So can I write this total property or the total quantity of that property in the control volume? Can I write this as integral over the control volume, total integral over the complete volume? Let us suppose if you take some small block, then the quantity that is present in the small block is basically rho times dV, which gives you mass, small elemental mass, into beta. So this gives you the property, you are integrating that. So can I write this expression? So please tell me, can I write this? Rho dV is the small mass that is actually existing, means in the control volume you have taken some small mass. Okay, so this rho into dV gives you small mass, and this small mass into property per unit mass gives you the property which exists in the small amount of space that you have considered. So if you integrate it, you will get the total property of this control volume, correct? What I am trying to tell you is, basically we have considered some small element of mass in the control volume. Say for example, somewhere here we have considered some small element of volume in the control volume. So rho into dV gives you small mass. Okay, so that small mass into this beta, quantity per unit mass. So quantity per unit mass, you are multiplying with mass, then mass and mass gets cancelled, you will get the property value in that small region which is present actually, correct? So that's how, if you see, this B of the control volume can be written in this way, B of the control volume. Okay, now so this is actually the control volume. Now if you see B3, we have to write certain important things here. B3, so this B3 is nothing but the system quantity which is present in this third location, okay, third region. Now tell me one thing, whatever is the quantity that is present in this third part is nothing but the quantity that has crossed this control surface and came out in a time dt, yes or no? Within the small time delta t, whatever is the property, whatever is the system that is actually crossing this particular thing, actually if you see this particular surface, if you see, for example, if I call this control surface 3 for example, okay, so let us suppose if this is control surface 3, for example CS3, let us suppose if this is control surface 3, then this quantity which is present in this region is nothing but the quantity which has cut this control surface and came out in a time of delta t, correct? So can I write that quantity as integral over the control surface 3? Now what is the mass that came out actually if at this location at any point if I take n cap is the unit vector, for example. So let us suppose if this is the n cap direction and if this is the velocity, relative velocity direction of the flow, and this is n cap, then the mass flow that comes out through small area is nothing but rho times of v bar dot n cap dA. This is the small elemental mass flow rate. Okay, so the mass flow rate that is coming out is basically this much. Okay, so this is the mass flow rate which is coming out. So in a time of dt or basically delta t, what is the total mass that comes out in a small time delta t? The total mass that comes out is actually this total mass, correct? Because this quantity rho v bar dot n cap dA is the mass flow rate. Okay, so with it per unit time, this much amount of mass is actually coming out. Okay, so whenever this much amount of mass is actually coming out, then in a small time delta t, this is the total amount of mass which actually comes out of that control surface, correct? And this quantity which is coming out is beta per unit mass. So for this much amount of mass, the quantity that comes out of the control surface is into beta. Did you all understand this expression, how I have written this? So this is the mass flow rate. So within a small time delta t, this is the total mass that actually comes out, and the quantity per unit mass is beta. So from that particular control volume in a small time delta t, this is the total quantity which is coming out in a small time delta t, correct? This is my mass of the system which is actually coming out of the control surface, of course upon integration. So if you see, this multiplied with beta gives me the total mass flow which is coming out actually. Okay, look again, I'm repeating, this is the mass flow rate. So mass flow rate multiplied with the time gives you the total mass which is crossing this control surface, and the total mass which is crossing this control surface multiplied with this property per unit mass gives you the total property which is actually coming out of that control volume in then this to the control surface thing, correct? Now at the same time, what happens here, whenever some through this control surface if some property is actually flowing out, then to this control surface 1, what's happening here? To this control surface 1 which is present here, to this control surface 1, to this control surface 1, some mass is actually flowing in, correct? So obviously, let us suppose if my system which is initially at this point is flowing out, then immediately the next particles which are here will start entering, but they don't come under my system. But if you want to calculate what is this B1, then this B1 is nothing but, again, B1 is nothing but, this B1 is equal to this integration over the control surface CS1, basically, again, rho times v bar dot n cap dA times delta t multiplied with beta. But here we know this n cap is always the unit normal vector which is outside, but here in this case this n cap at this locations, if you see, this n cap is in this direction. Okay, n cap is in this direction in yesterday's case we have seen, and the velocity of the flow is in this direction. So definitely what happens, this is n cap and this is v bar, so the angle between these two will be obtuse angle. So definitely for the inflow we know we have kept a minus sign. Okay, so this minus actually denotes that, this minus sign actually denotes that system, basically if you see, this is minus sign because we have seen n cap and v bar are in opposite directions. Opposite, or generally instead of opposite you can say are in let us, instead of telling it in n bar and v bar, let us write one thing. This is due to the mass flow into the control volume, into the control volume, mass flow into the control volume. Why we have taken a minus? Because n cap is the outward normal vector. So for any surface it's the outward vector, but this velocity which you are taking b1 is nothing but we have considered about the quantity which is actually entering this system actually. Okay, so that's how, if you see, this minus sign is due to the mass which is actually flowing inside. Okay, because this n cap is outward to the surface and the velocity is such a way that the fluid is coming into the surface, so that's why there is this minus sign. Okay, now if you see this b3 minus b1, therefore this b3 minus b1 gives you B3 minus this B1 actually gives you this thing. Integral over the control surface CS3 rho times V bar dot n cap dA. This is the mass flow rate into delta T times beta. This is the total minus this quantity. So minus of minus gives you plus actually. So minus of minus gives you plus integral over the control surface 1 rho times of V bar dot n cap dA into delta T times of beta. So this is what you have. Clear? Because this is a plus sign, because B3 minus of this B1 has one more minus. So minus of minus becomes plus. So this is what you have. Here we have assumed that the control volume is actually fixed at one location, but if control volume is also moving, then all these velocities, whatever we are writing here, these are relative velocities. Okay, so these should be relative velocities, because you know, if volume is also moving, then mass cannot enter at the same mass flow rate. Okay, only some part of the mass which is traveling will be able to enter because the control volume is moving. Okay, so in all these cases it is a relative velocity if the control volume is also moving. Okay, now this can be written as, since you see this combination is same, this control surface 1 and control surface 3, if you write it as a total, this control surface 3 plus this control surface 1, total it is nothing but the control surface of the volume that you have taken, means the surface of the volume that you have taken. So therefore this is equal to, this implies B3 minus B1 is equal to integral over the total control surface rho V bar dot n cap dA times delta T into beta. This is over the total control surface. Now let us suppose if we substitute this in the limit, let us see what we get. Limit, therefore limit delta T tends to 0, B3 minus B1 by delta T. So this quantity is equal to limit delta T tends to 0. Now B3 minus B1 is this value which you have identified, integral over the control surface rho times of V bar dot n cap dA is what you have as the mass flow rate, multiplied with delta T into beta. So this quantity divided with delta T, correct? This is the limit that you have. Now in this integration is with respect to this small area that you have taken. Delta T has nothing to do with this integration. So let us suppose if you take this delta T out of this integration, then we can do one thing, this delta T and delta T gets cancelled actually, correct? So now there is no delta T to apply. So this expression is nothing but integral over the control surface rho times beta. If you see, rho beta into V bar dot n cap dA, or generally this is written in this form, beta times rho V bar dot n cap dA. So this is what you have, and this is the total mass flow rate, or the total mass flow rate which is actually crossing the control volume. Okay, so if this is the net mass flow rate which is crossing the control volume, then this multiplied with beta gives you the net quantity which is crossing the control volume, correct? So this is net mass flow rate, net mass flow that crosses the control surface, okay, so that crosses the control surface actually. So this is the net mass flow that actually crosses the control surface. So if this is the net mass which is crossing, so this multiplied with this property per unit mass gives you the net quantity which is crossing the control volume actually, okay, control surface of course. Okay, so now if you see this relation, this equation which you have started here, this dB by dt of the system which is split into two limits, here you can see we have split it into two limits. So for the first limit we got the answer, for the second limit we found what is the answer. So therefore dB by dt of the system, therefore dB by dt of the system is equal to dou by dou t of integral over the control volume rho times of beta into dV plus integral over the control surface beta times of rho V bar dot n cap dA. So this is what you have for the total change in the system and control volume relation. Okay, so this is basically the relation between change in property of the system or change in quantity or property. Generally, if you take like mass, whatever you take, so property of system to change in control volume, to change in control volume, to change in control volume. So this is the equation that actually comes out, and this equation is basically the Reynolds Transport Theorem. Okay, so Reynolds Transport Theorem tells you that, basically, I'm just writing the statement here, rate of change of quantity, rate of change of quantity of a system is equal to rate of change of quantity of control volume, rate of change of quantity, rate of change of quantity of control volume, rate of change of quantity of control volume plus this is nothing but the net rate of efflux. You can write net rate of efflux. Efflux is nothing but this property beta which is present actually. So net rate of efflux that crosses the control surface, that crosses the control surface, that causes the control surface actually. Okay, and this is the Reynolds Transport Theorem which actually gives it. So rate of change of quantity of any system is equal to rate of change of the quantity within the control volume plus the net rate which is actually exiting or entering, basically the net efflux or the net rate which is actually leaving the control surface. Okay, because we have talked about leaving, we have taken a positive sign for the outward vector, so this is basically that crosses the control surface or leaving the control surface in general. Okay, so this theorem which is here is actually the Reynolds Transport Theorem actually. Clear? So this is one very important and good thing that actually tells here. So if you summarize this, RTT actually gives you something like this. If B is any property, if B is any quantity of a system, any quantity of a system, for example, say like mass, momentum, angular momentum, whatever you see, mass, momentum, angular momentum, whatever, etc. So if you see mass, momentum, this, and beta is the quantity of system per unit mass, quantity of system per unit mass, then we know that rate of change of, then we know that this rate of change of quantity of system is equal to rate of change of this control volume property, which is nothing but beta times of rho dV, beta times of rho dV. This is the volume change plus integral over the control surface, rho times or beta times, let us write beta first, beta times rho V bar dot n cap dA over the total control surface if you integrate this quantity. So this is the equation for this, and here in this case we assumed that basically, if see, we assumed that this control volume is at one particular location. Okay, so control volume is not leaving, so that's why we have written velocity vector. If control volume is also moving in general, we will get this relative velocity here. Okay, so VR is relative velocity of system, relative velocity of system with respect to control volume. With respect to control volume actually here. Okay, so with respect to control volume. Okay, so this is what you have basically here. Okay, so this is the case. So if you take this, then this is the Reynolds Transport Theorem that actually gives you, and this equation is the fundamental Reynolds Transport Theorem equation. Okay, now if you apply this equation to different quantities, like for example mass, momentum and all, we will achieve the conservation equations. Okay, so let us see how we will actually apply that. So see here, conservation of mass. So first of all, let us apply this to the conservation of mass. So let us take our first quantity B is mass, for example. Okay, so B is equal to mass, then what will be beta? This implies what is beta value? If B is mass, then quantity per unit mass, so mass divided by mass, what will be the value of beta? What will be the value of beta? If B is M, I told you beta is actually B divided by M, correct? Mass of the system. So please tell me, if I take my quantity as mass itself, then mass by mass, what is the value? 1, correct? So beta value is 1, correct? Because if you see here, we have defined that beta is actually this capital B divided by mass. So here if you take this capital B as mass, then your beta value is equal to 1 in this case, correct? So this is 1. Now if you see one thing, if you apply Reynolds Transport Theorem, let us write here, applying RTT, applying RTT, Reynolds Transport Theorem. So here guys, look, this is a scalar quantity, correct? So this is a dot product of two vectors. So this is scalar, which is nothing but the mass flow rate. Okay, now let us see what comes out. dB by dt of system is equal to dou by dou t of integration over the control volume, integration over the control volume, dou by dou t of integration over the control volume, beta. So beta value is, first of all let us write the thing, beta times rho dv. Let us first write the theorem, then we will substitute. Okay, integral over the control surface, beta times rho v bar dot n cap dA is what we have seen, correct? Now if you substitute this, beta is equal to 1 in this case. I want to ask you one thing. Look, mass I have taken as the system itself, correct? So system is nothing but some quantity of matter. So whenever I have taken my system, I have already chosen my particles. So some new particles, if it enters the volume, that won't be my system. So now if you see, when I say mass of the system is m, for example, then what will be the rate of change of mass of my system with time? Please tell me. I have already identified these particles are my system. Okay, now whatever might happen, I'm not going to change my particles. These are the particles. So can you please tell me, as time happens, as flow happens, the system inside the control volume may decrease or increase, but my system will not change, correct? So when system is not changing, what is the rate of change of mass of the system? Means if I take B as mass, what is the rate of change of mass of the system when system is not changing? So please tell me. My system is actually the mass which is actually available, correct? So please tell me, what is this dB by dt of the system? Any idea? 0, correct? Obviously it is 0, correct? Because if you see, my system is those set of particles. So even with time is changing, I am not changing my particles. So my mass of the particles remains fixed. So that's why here if you see, this quantity is basically 0. Okay, so let us replace here. Okay, let us write one more line, for example with mass. So this implies dm by dt of the system is equal to dou by dou t of integral over the control volume. This beta value is 1, so that's why rho dv plus integral over the control surface, beta is 1, so rho v bar dot n cap dA. This is the case that you have. Okay, so this is the case. Now here if you see, for mass, this dm by dt of the system is actually 0, because mass of a system is fixed. Mass of a system is fixed. Mass within the control volume can change depending upon inflow and outflow, but mass of a system is fixed. If I fix some matter, then the mass of the matter is actually fixed, है ना? So mass of a system is fixed. Now let us see what comes here. This is the equation. So here if you slightly apply one thing, In yesterday's case also we have seen if this dA is closed, we have seen this equation actually. So this implies 𝐂 is equal to, or you can write dou by dou t of integral over the control volume rho dV plus integral over the control surface rho v bar dot n cap dA. This is equal to 0 is what you have written, correct? So this is the case. So this is the equation which is actually a continuity equation that we have seen the other day. Now if you see, let us suppose there is some control volume. Now into that control volume, let us suppose that control volume is operating at steady state. Okay, so let us suppose if control volume is at steady state, if control volume is at steady state, if control volume is at steady state, what is the meaning of this? If control volume is at steady state, then what is the meaning of this? D by dt of mass of the control volume means with respect to time this cannot change, with respect to time any property cannot change, correct? Energy of the control volume will be 0, so anything will be not change. So please tell me, whenever this is at steady state, can you tell me dou by dou t of some quantity, so rate of change of this quantity with respect to time. So please tell me what will be this value. If control volume is under steady state operation, let us suppose you take some pipeline or something, what are the fluid that's coming in, same amount of fluid is actually leaving out. In case of steady state operation, variation of any quantity with respect to time, so what is this value? Variation of any quantity with respect to time in this case. So please tell me what could be this value. What could be this value here? Variation of any quantity with respect to time. Okay, so this is 0, correct? So this equation is also 0 because this is rate of change of time. Therefore your equation implies integral over the control surface rho times of v bar dot n cap dA. So this quantity is equal to 0 for steady state. What is the meaning of this? Net mass that is crossing the surface is actually 0. The meaning of this is whatever the mass that is coming in, same mass should go out. That's it. Okay, we initially know this from our understanding of steady flow, but you know in this case the net mass flow over the control surface should be 0. Means what is the meaning of that? Whatever mass is leaving from some portions of the control volume, same mass should also leave, same mass should also enter the control volume from some other locations actually. Okay, so this is actually the steady state. Okay, so this is steady state, and this meaning is net rate of efflux. Net rate of efflux means basically any property, net rate of efflux across the control surface, across the control surface is 0. Meaning mass entering, because we have taken the property beta, so mass entering the control surface should be equal to mass leaving the control surface. Okay, so this is equal to the mass leaving the control surface. Clear? So this is the net understanding of the Reynolds Transport Theorem when you apply it for the mass. Okay, so you see we got this understanding. So from this understanding, this rate of mass is of the system is actually 0. So this is equal to all the things that you have taken. Okay, so these are basically the cases. Okay, so now let us apply it for the momentum, linear momentum case. Let us see what comes out. Okay, so let us apply for the conservation of momentum. Let us see what comes out. Okay, so momentum, so quantity here is momentum, so quantity is momentum. Okay, momentum, so this implies your B is equal to m into v bar. Let us suppose if m is the mass of the system, it is moving at some relative velocity vr. Okay, so if you write vr, okay, relative velocity with respect to the control volume, this system is moving at some relative velocity vr. So this implies beta, which is b by m, which is v mass into relative velocity by m. So this m and m gets cancelled, so beta is actually equal to relative velocity vector. This is the relative velocity vector. Okay, so this is the expression for beta. Okay, now if this is the expression for beta, now let us apply Reynolds transport theorem. Applying Reynolds transport theorem, applying Reynolds transport theorem. So what is Reynolds transport theorem? dB by dt of any system is equal to, system is actually some quantity of mass, correct? So dB by dt of the system is equal to dou by dou t of integral over the control volume beta times of rho dV plus integral over the control surface beta times of rho into V bar dot n cap dA, correct? So this is what you have actually. Okay, so now if you see this quantity, this is nothing but rate of change of momentum of the system. System is nothing but some mass, so this is nothing but rate of change of momentum of the system. So this is equal to dou by dou t of integral over the control volume, beta is V relative rho dV plus integral over the control surface V r bar times this rho into V r bar dot n cap dA is what you actually have here in this case. Okay, so this V r bar dot n cap is nothing but the mass flow rate. So this is equal to the mass flow into net mass flow, of course, into this velocity. This gives you the momentum actually that's leaving. Okay, so now if you see, look, you know, whenever I'm telling system is nothing but some quantity of mass actually, so if that's some quantity of mass, the rate of change of momentum on mass is nothing but given by Newton's second law of motion, correct? So rate of change of momentum of any mass is equal to the net force which is applied on that mass. Yes or no, correct? So please type in the chat box. Is this clear to you? From Newton's second law, let me write here. From Newton's second law, we know rate of change of momentum, or you can say force applied on net force. You can write better, net force. Net force applied on any system, basically some mass which is fixed actually, some mass which is fixed is equal to rate of change of momentum of the mass, basically the system, correct? This is what we have as the Newton's second law. Now if you see, this is nothing but rate, this is momentum, so rate of change of momentum of this particular system. So this actually gives you net force acting on the system. So this is equal to, just a minute, I think this is okay, fine. So this is equal to net force acting on the system is equal to, means let us suppose if fluid is flowing, then the fluid, net force acting on the fluid, for example. Okay, so this is equal to, net force acting on the system is equal to this component dou by dou t of integral over the control volume velocity vector times rho dV plus integral over the control surface V r bar, okay, here also it's relative velocity dot rho V r bar dot n cap dA. So this is what you have. Now under steady state, so let us suppose if there is some plate, so some amount of fluid is going, hitting and coming back. Okay, so let us suppose the mass flow of the fluid is some constant. Okay, everything is constant, it's steady state. So now let us suppose if this is steady state, at steady state, so if you see at steady state, this dou by dou t, rate of change of this quantity V r bar times this rho dV. this quantity is basically 0 in this case. Okay, so this is basically 0 is what you have here. So this is 0. So whenever this quantity is 0, means the rate of change of control volume is basically 0. This implies, because this is time rate of change. Okay, so steady state, this term is actually 0. So whenever this term is 0, we know net force acting on the system, means basically normal in our case fluid will be our system because fluid is flowing. So if you want to select some mass, you will select some mass of the fluid, correct? So net force acting on the system is equal to, if you identify this, look, I have to tell you one thing here. Over the control surface, relative velocity vector dot rho v r bar dot n cap dA. Now I just want to ask you one thing. This is mass flow, this is VR. So can I say this is nothing but the momentum, net rate of momentum that is leaving the fluid? Yes or no? So what is net rate of the momentum that actually leaves? You can write that as mass V relative out minus mass flow, because you see this is the expression of the complete control volume. If you see, this is the case. So m dot times VR in, because you see the net rate is actually in this case. Okay, so let us write, instead of this out only for R, we'll write this at outlet minus V relative velocity at inlet. Okay, so this is what you have. So this gives you the net amount of momentum which is actually leaving the control surface, correct? So if you see integral over the control surface, this n cap we have taken outward vector, so that's why net which is leaving out. Okay, so that can be written as mass flow. This is actually a scalar quantity, so that scalar quantity times this V r bar gives you m dot V r bar at out minus m dot V r bar at inlet. Okay, so this is how we have the things clear. So therefore net force acting on the system, net force vector. Okay, so all these are vectors, we are using vectors in the story, so fine. So therefore if you see net force acting on the system is equal to, we can keep it like this. If you see integral over the control surface, because sometimes what happens, a single outlet will have or a single inlet will have two outlets. At that points we need some understanding. So integral over the control surface V relative velocity dot this rho V r bar times n cap dA, which is actually equal to this equation which is present here. So let us not write this. This equation is the ultimate equation. Okay, so anyhow if you see, this equation is the final equation that you can talk about. Okay, so this is the equation which is present for you. Okay, so now this is the equation. Now one important thing here is you can write in words if you would like to. So see here, net rate of, or the net force acting on a fluid is equal to, obviously you can understand, this is equal to rate of change of the momentum of the fluid. So this is something which is important, which I told you yesterday, that we have seen from the Reynolds Transport Theorem. Okay, so rate of change of momentum of the fluid, but provided it should be under steady state. Okay, so otherwise this term will also have some importance here. Okay, so right now in general at gate level we deal with only steady state systems. So rate of change of the momentum of the fluid is what we have. Clear? So this is the linear momentum equation that actually comes out. Okay, so this equation is called, you can write this equation is linear momentum equation. Linear momentum equation is what you have. Okay, so this is the linear momentum equation is what you have here. So basically if you see This equation we have seen from the Reynolds Transport Theorem. So if you apply this Reynolds Transport Theorem for the momentum of the flow, then you can get it this way. Okay, so we will see in next lecture, we will see lot of applications of this linear momentum equation and angular momentum equations. Okay, so all your doubts, why this v is substituted as v minus u, why there is plus sign, why there is minus sign, why you have taken this as positive, this as negative, we will talk about all these things in applications of this. Next lecture is completely dedicated for this applications of linear momentum equation and also the angular momentum equation. Clear? So there we will see lot of understanding of all these things. Now let us see here. This statement is much important. So the net force acting on a fluid is actually equal to the rate of change of momentum of the fluid that's actually going in the control volume. Okay, now let us see the case of angular momentum. Okay, so let us see the case of this angular momentum. So conservation of angular momentum. So let us see here. Conservation of angular momentum. So let us suppose there is some plane like this. Now let us suppose you have an axis, for example, which is perpendicular like this, for example. Say, okay. Now let us suppose if there is some particle which is rotating. Okay, so let us suppose there is certain particle which is actually rotating here along this fractal kind of thing, for example. Okay, and this is the z axis, for example, and this is some xy plane. Okay, so this is some z axis and you have your xy plane, for example. And let us suppose if there is some particle which is at this location, this particle is actually rotating. Okay, so I have taken system should be some mass. Okay, so I have taken some small particle to identify some small fluid block which is moving at some velocity. Okay, now if you see this, the velocity of this particle is something like this. Okay, so if you see, the velocity of this particle is something like this. So the momentum of this particle is m into v bar. This is the momentum of the particle. Okay, now if this is momentum of the particle, for example m v bar, then let us suppose this is the radial vector that's connecting these two, for example. Okay, so this is r bar actually in this case, and this is the axis about which this particle is performing some rotation in this plane. Then you know angular momentum normally denoted with L bar in this plane is equal to R bar cos mv bar. Correct? Yes or no? So please type in the chat box. Have you seen this? Linear angular momentum is basically R bar cos this momentum vector. So you know angular momentum is nothing but moment of the momentum of the particle. So which you might have seen in engineering mechanics course normally. Correct? Have you seen this? So please type in the chat box. I think Yuva cannot comment. Yeah, Yuva's comments are not coming, I think. Fine then. Okay, so fine. So please comment. Yes, you might. Okay, you're commenting. Good. So fine then. So this is actually the angular momentum case which you might have seen. Okay. Now if this is the angular momentum, so now let us suppose if B is this case. So B is equal to R bar cos m v bar actually. Okay, so we have this R bar cos this m v bar. Okay, sorry, R bar cos rho. Okay, momentum you are denoting with rho maybe, I think, but normally this is the momentum that happens for any particle traveling at velocity vr. So this is the case. Okay, so this implies beta. What is the value of beta? B by m. So this gives you R bar cos momentum. This is vectors. So R bar cos momentum vector by mass. So here if you simplify this, mass and mass gets cancelled. So this implies beta is equal to R bar cos this v bar actually. Okay, so this is the vector which we have. Now apply Reynolds Transport Theorem again. So applying RTT. So let us suppose there is some fluid which is actually going under some evolution. Normally in case of turbines, you know, in case of pumps, what happens? In case of radial entries and all, fluid actually rotates. Okay, so fluid particles, some fluid will enter radially and it actually rotates and leaves out. Okay, so in case of turbines and all, generally we have this. Okay, now if you see, if you apply, and also in some cases like lawn sprinklers, which is like radial flow reaction turbines and all. So we see applying RTT. Now if you apply this Reynolds transport theorem, let us see what comes out. Okay, so d by dt of this angular momentum, which is r bar cos mv bar, is equal to dou by dou t of integral over the control volume r bar cos v bar times rho dv. Okay, this is volume. Let us denote this with v because this velocities are also there here. So this is of course the relative velocity normal. Okay, let us suppose if this plane is also moving, then if this plane is also moving, sometimes what happens whenever the fluid is trying to flow, this frame means, let us suppose if you take the case of a lawn sprinkler for example, then in such case what happens, the fluid, let us suppose if this is arm, fluid is coming radially and being sprinkled all over. Okay, so in such case what happens, when fluid is traveling along the arm, then definitely this arm also rotates. Okay, so that's why we are talking about the relative velocity. Sometimes this plane can also rotate along with this particles, and then there is some relative velocity. Okay, so let us suppose we write vr for example at every location wherever there is velocity, let us write relative velocities. Okay, so relative velocity, so this is equal to rho dv plus integral over the control surface this beta, which is let me write the term slightly bottom because this is coming obstacle. So integral over the control surface r bar cos this v r bar multiplied with rho v bar dot n cap dA. So this is what you have. Okay, so this is the expression. Now if this is the expression, now rate of change of angular momentum of any mass, what is it equal to? Rate of change of linear momentum on any mass is equal to net force applied on the body. Similarly, this rate of change of angular momentum of any mass is equal to what? You might have learnt in rotational mechanics. Since engineering mechanics course got finished for you, you might have definitely learned there. So please type in the chat box. Torque, correct? Net torque. Okay, I'm calling it net because there could be n number of torques such that they produce some net effect. Okay, so net torque. Okay, so the rate of change of angular momentum, the rate of change of angular momentum, the rate of change of angular momentum of a body, or generally mass of some mass system. Okay, of a system, you can write system instead of body because our aim is to talk about some finite mass. Okay, of a system, some finite mass is equal to net torque acting on the body or acting on the system. Net torque acting on the system actually, correct? So this is basically equal to the net torque. So therefore let us write, therefore d by dt of this small r bar cross mv bar, this is equal to net torque that actually acts on the body. Okay, so net torque that actually act on the body. So therefore sigma t, this implies sigma t is equal to, torque is basically some vector. Okay, vector quantity, has certain direction and all. So net torque is equal to, now this equation if you write dou by dou t of integral over the control volume r bar cos v r bar times rho dv. This volume I'm using a cut because velocity and all you will get confused otherwise. So this quantity plus integral over the control surface this small r bar cross v r bar times, we have this rho v r bar dot n cap dA. This is anyhow the mass fluid that actually turns out. Okay, so now if you see this at steady state, again at steady state operation, if you see at steady state at steady state, what you have basically here, at steady state, this rate of change of this quantity with respect to time is 0. So dou by dou t of any quantity is 0. So dou by dou t of this control volume r bar cos this v r bar into rho dv. This is 0 actually. Okay, of course 0 bar you can write because this is vector actually. So vector quantity, if you write, this is 0 bar. Similarly, in case of force term also, I think I have kept only single 0, put a bar here. Okay, so this is 0 bar. Okay, so now if you see, this is 0 bar. Now if you see this, this implies net torque acting on the system, means basically fluid is your system, for example, then net torque acting on the fluid, for example. So this is equal to, net torque acting in the fluid is equal to, now if you see this equation, this is total control surface. If you take this over the control surface, this r bar cos v r bar into rho v small r bar dot n cap dA. So this is the total expression which is available. Okay, here if you apply, this is a scalar quantity, dot product of two vectors, mass flow rate. So this is mass flow rate, and also let us suppose if this angle between these two is 90, means radial and tangential components, let us suppose, then definitely what happens, the angle between them is 90. So this magnitude becomes, this is m dot mass flow which is actually there, and this smaller bar cos VR bar. Let us suppose if you see, rotations are always due to the tangential components, correct? Means let me explain you. For example, let us suppose I have taken this bottle, for example. Okay, now when I take this bottle cap, for example, this is circular in shape, then this is the axial direction, this is the radial direction, and this is the tangential direction, correct? Now out of these three components, let me draw on board, let us try to understand something. So see here, let us suppose you got a disc, for example, something like this. Okay, so let us suppose you got a disc, for example, this is center of the disc. Okay, if this is center of the disc, this is actually the basic funda for this hydraulic machines also. So now if you see, I just want to give you one thing. So now let us suppose if this is some disc. Okay, we have some axis of the disc. Now try to understand something. You have applied some radial force along the disc, along the center of the disc. You have applied some axial force along the axis of the disc. You have applied some radial force along the axis of the disc. So this is F axial, this is F radial, and this is F tangential. For example, let us suppose if there is some force which is hitting it tangentially. Okay, so at the tangentially, something like this. Okay, maybe at some radius. So let us suppose you have some radius to this particle. This is F tangential. So out of these three components of force, let us suppose if there is some fluid hitting the water. Let us suppose if you have some turbine, your turbine has some rotor, then your fluid is actually trying to rotate the turbine. Okay, so your fluid is going and hitting the rotor. Okay, now if your fluid is hitting at some force F, let us suppose if these are the three components, one is along the axis of the wheel, one is along the radial, and one is actually tangential. Now tell me, out of these three components, which component is actually responsible for the rotation of the wheel? Actually, out of these components, which component is responsible for the rotation of the wheel? Out of these three components, out of these three components, tell me which component is responsible for the rotation of the rotor whenever some fluid is going and hitting? Obviously tangential component, correct? So here this tangential component is responsible for the rotation. Okay, and you know one thing, tangent and radial, look, whenever some, look, let us suppose if this is the disc, for example, look, see here, if this is the disc, for example, okay, let us suppose if this is the disc, okay, this is the axial direction perpendicular. So if you see, this is the axial direction, this is the radial direction, and tangential is something like this. Okay, if I want to rotate this, I have to apply a tangential force, correct? Na? A radial force will pass through the radius, so it don't have any basically moment that can rotate this disc actually, or the rotor, whatever is available. So tangential component is the component which is responsible for the rotation of the things. Okay, so now if you see this case, this tangential component is responsible for rotation. Okay, Shrikant, clear? Now this tangent and the radius at any given location are perpendicular to each other, correct? Yes or no? You know the radius of the circle, axial also will pass through the center of the disc, correct? So that also don't produce any rotation, you know? Axial component will also pass to the center, so it cannot produce any moment or torque that can rotate the wheel. Okay, axial and radial will both pass to the center, correct? Okay, so clear? Okay, now you know if you take any circle, then the radius and tangent of that circle are perpendicular to each other. So whenever this is perpendicular to each other, then can you tell me, can I write this as R into VR normally? R into VR, and this is mass fluid. So this is nothing but m dot. Okay, so this is nothing but the angular momentum, net rate of change of angular momentum of the fluid. Okay, so net torque acting on the fluid is equal to the net rate of angular momentum change of the fluid, or the net angular momentum which is leaving out. So that you can write as net force, or sorry, net torque acting on the system is equal to m dot v relative into this mvr is what we have. So mvr, of course I am just writing this thing. So out at outlet minus m dot v bar dot r at the inlet. Okay, so this is how we get the net torque acting on any fluid. So net torque acting on any fluid system is actually equal to this quantity. Now I will ask you one thing, so please tell me this: whenever you take a turbine in general, for example, if you take a turbine, normally in case of turbines you might have observed that normally if you leave the impulse turbine, if you see radial turbines and all, we have this important property that in case of normally if you take two devices, first is turbines and second is, let us suppose, if you have some pumps for example. Okay, in case of turbines you generally experience this: fluid enters at higher radius and leaves at small radius. Have you ever observed this? Means if you take any Francis turbine or Kaplan turbine, generally, let me show you. I don't know, you might have seen a Kaplan turbine still, so but let me show you Francis for example. If I teach hydraulic machines, I will definitely do that, but Francis turbine. Okay, so let us suppose if you see a Francis turbine for example, images I will show you, you can get some better idea. So this is basically a Francis turbine actually. Okay, so if you see, this is a Francis turbine, top view, all these are Francis turbines. Okay, so now if you see this Francis turbine working for example, wherever you see anything, so my intention is to tell you that one thing: if you see this example, for example, this is much better, it is given in a good way. So if you see this turbine, you can understand one thing: from the center of the axis, if you see one thing, this outlet is at higher radius and basically inlet is at higher radius, and outlet, the fluid will slowly enter through the spiral casing and it will fall into this radial shaft which is present, actually radial opening that is present. Normally in your lab and all, you might have seen the Francis turbines, they will be mounted on the horizontal floor actually. Okay, so the jet enters the turbine blades from the outlet, and actually this is a spiral casing, it's not completely circular, this will be spiral actually. Okay, means as it comes towards this end, the cross section will keep on decreasing. Okay, so it is tapered. The reason is, mass fluid will actually decrease by the time fluid actually travels, because meanwhile fluid enters this, so whatever is the mass that's available here, same mass will not be available here, because some mass will already enter the blades in the meanwhile. Okay, so whenever mass fluid is decreasing, but if you want to maintain the same velocity of the fluid, because velocity is important, okay, impact of the blades with the fluid is much important. So if you want to maintain the same velocity but mass fluid is actually decreasing, then what is the alternative? You have to decrease the area, because of course it's incompressible flow. So now if you see, when mass fluid is decreasing, when discharge is decreasing to the path, then to maintain the same velocity, what we do is generally, instead of putting a circular tube, you will have a slightly tapered, means basically from here, when you try to start coming towards this location, the cross section of the flow basically decreases. You might observe in your labs next time when you go to any hydraulic machines lab. In case of transist turbine, this casing will be spiral, it won't be circular. Okay, so it will be like a spiral basing, which actually reduces the flow towards this direction. Anyhow, the main story out of this is, in case of reaction turbines where this impact angular momentum is important, what we understand is, at this point, inlet to the fluid will be higher radius and outlet will be smaller radius. Okay, the reason for this is, look, m dot is same generally in both the cases. Okay, so m dot will be same, but one very important point is, when fluid is impacting the turbine, net force acting by the fluid on the rotor should be positive, correct? Normally in case, what happens, energy given to the system is taken as negative, correct? Heat given to the work given to the system, all these things are taken as negative generally. So if you see, main thing is, in case of turbines, this inlet will be at higher radius than outlet. The reason for that is, look, whenever fluid is going and impacting the rotor, net torque or the net momentum change of the fluid should be negative, means the force given to the rotor should be positive, correct? The energy which is given to the rotor should be positive, then only it will rotate, correct? So if force applied by the fluid on the rotor is positive, then definitely force applied by the rotor on the fluid should be negative quantity actually. Okay, means this should be negative quantity. If this has to be a negative quantity, this term should be more, because velocities, they don't change much within that small range. Okay, but here if you see, this R inlet should be high, so that this net torque acting on the fluid is negative, so that net torque acting on the rotor is positive. Understood? So that's how it facilitates the rotation of the wheel. Clear? So let us write one statement for that. In case of turbines, in case of reaction turbines, if you if you try to identify this, you will see, in case of reaction turbines, your fluid at outlet, means radius at the inlet of flow is greater than radius at outlet of flow. This you can see, I have shown you in one diagram, but normally you can see this in any labs and all. If you go, you will easily understand that. Okay, so net torque that is acting on the rotor should be positive to start the rotation of the rotor. Okay, so that's why this radius at inlet is generally high in case of turbines and all. In case of pumps, the case is reverse. Okay, in normally you might have observed pumps. In case of pumps, fluid enters from the lower radius. Okay, normally if you take any centrifugal pumps or something, what happens, fluid enters the pump from the least, not least but lower radius, and at the same time it exits from a higher radius. You might have seen this. Okay, I'll show you, maybe if there is some pump I can show you. So centrifugal pumps I can show you, for example. Centrifugal pumps. Okay, I'm not going into much details because we deal them separately in a hydraulic machines course, which I think maybe not me, maybe some other faculty will take for you, I don't know, but generally this happens. Okay, normally when you take any pumps, we have a lot of things called the characteristic curves, all these things. The main thing that happens is, in case of pumps, definitely your inlet will be at lower radius compared to the outlet. Okay, so that should happen. Like for example, you see any pump and all. Okay, so you see here, see, you can see here they have clearly shown you working principle and all, but right now I'm just showing you the diagram. Okay, maybe some diagram is taking some time to get loaded. Okay, so I think it's taking some time to get loaded. Okay, so but the main idea is, okay, I'll explain you somewhere here where we can see the diagram. At least you can see inlet is given from this location, outlet is given at higher radius, correct? You see, whenever the fluid is entering in, the radius is actually low, and at outlet this is actually having higher or larger radius, basically, because there the story is different. Torque, normally what happens, okay, in a pump, rotor will actually deliver some energy to the fluid, and the fluid will go to certain height or something like that, right, at some pressure, basically. Okay, so that's why in case of pumps, what happens, energy is supplied by the rotor to the fluid. Okay, so in such case, the net torque acting on the fluid should be positive. Okay, now if this quantity has to be positive, net torque acting on the fluid should be positive, then this has to be a higher value and this has to be a lower value in that case. Okay, so that's why normally if you observe all these things, you will understand it in a better way physically outside. If you see, in case of turbines, this radial at inlet of flow should be greater than radius at outlet of the flow. Similarly, in case of pumps, if you see, in case of pumps, radius at inlet of flow is generally less than radius at outlet of flow. Normally in some interviews they can ask you if they want, of course not to this level they ask you, but still if you go to interviews like BARC or something like that, then you can get these kind of questions. They'll ask you, in turbine, inlet will be at higher radius or outlet will be at higher radius. We'll feel very difficult in answering if you never seen a turbine actually. Okay, so in your labs and all, I think definitely they might be installed, they might have installed some Francis turbine, Pelton wheels, all these things. So when you find some time, go to lab. Okay, so you will understand all these things in practicality, because here I can show you just images. Okay, maximum I can play some YouTube videos, that's it. Otherwise I cannot show. But anyhow, when we go for some hydraulic machines course, maybe okay, I may not take it, but whoever takes it will definitely take you to these things, these fundamental things. But the main idea is to understand these things. Okay, so this momentum equations in this angular momentum is called the Euler's equation. Again, this is also given by Euler, so this equation is actually called the Euler's equation. Okay, so normally you see, have you seen this formula anyway? Head supplied to the turbine, H is equal to VW1 U1 minus VW2 U2 by 2G. You will get these formulas actually. Have you do you remember this? VW1 is called the tangential components actually. These are the tangential components which are responsible for the rotation of the rotor. Correct? You have seen this skin? Have you seen these things anywhere? Head developed by the turbine at the rotor. They might have given you these kind of things. Correct? So basically all these things, they depend upon this. Okay, so it's very important for you to identify these things. Okay, and also you see, in case of turbines, okay, this U1 and U2, U1 can be written as R1 omega and U2 can be written as R2 omega, or pi do whatever. If number of rotations is given, you will convert that to omega, 2 pi n by 60 and all. So you will see definitely your U1 values will be higher than the U2 values, except for the Pelton wheel, because in case of Pelton wheel, inlet and outlet occurs at the same radius from the center of the shaft. Okay, because that's an impulse turbine, there the principle is something different. Okay, it's not based on this reaction cases. So we have something called impulse turbine, reaction turbine. So there the case is something different. Okay, so in case of Pelton wheel, what happens? This U1 and U2 are same. What happens? It hit the bucket and it will actually comes out. On Pelton wheel, you will have a lot of buckets on the runner actually. Okay, so whenever the fluid hits the bucket, then the fluid gets splashed and it actually comes back in the same radius. Okay, but in case of Francis turbine and all, what happens? It enters at one radius and it comes out at different radius. Now, which radius is high, which radius is low, it depends upon this torque equation actually. Clear? And anyhow, this is just a basic understanding. In this course, we don't talk about the turbines. We will talk about only one particular case, which is the lawn sprinkler case, which is also some part of a reaction turbine actually. But we will see. Have you ever seen any Kaplan turbine in your life? Kaplan. Have you seen any Kaplan turbine in your case? Actually, we all have seen a Kaplan turbine. You know where? Look. Many of you might have seen this. Kaplan turbine is basically axial flow reaction turbine. So if you see, we all have seen this Kaplan turbine. Normally during childhood, you might have got this toy actually. There will be one small straw kind of thing, some plastic pipe, small pipe, okay, like the straw, cooling straw like kind of thing. Onto that there is one fan that is attached, correct? You will hold that fan and you will start running slowly so that the fan will rotate. Have you seen this anywhere? So if you see, normally this toy, I don't know what it's called in but normally there is a small plastic pipe kind of thing, then there is a fan here with so many vanes, some vanes kind of thing. So if you run basically, then this fan will rotate at high speed. Sometimes during school days and all, we used to keep it to cycle and then cycle at very high speed so that this fan will rotate faster. That's nothing but a Kaplan turbine. Okay, the jet engines which you might have seen normally outside, if you see these propellers, what are they? Those are also they actually whenever fluid comes and hits, they actually rotate. Okay, so basically normal in case of water, normal in case of boats and all, it is water, but normal in case of aeroplanes or choppers, if you see, choppers don't have the side vanes, but normally aeroplanes, if you see, they have this propelling fans. Okay, so they are also some turbines. Okay, so Kaplan turbine is basically axial flow. Okay, so in such case you may again ask me, sir, just now you told axial force cannot generate some rotation, then how axial flow turbine is developed? Axial flow also has certain tangential component of velocity. You see, if you take the blades of a fan, for example, fan blades are never straight, they'll be inclined at some angle. Have you seen this? Have you seen this anywhere? Normally if you put a table fan, for example Crompton or some other guys, the vanes will not be very straight, they are actually curved. Can you see this? Why there is a curvature? Because look, you can ask yourself this question. Let us suppose if you switch on a fan, you will feel some cool air onto you, correct? If you sit on the back side of the fan, will you get air? No, correct? Because obviously the design or the shape of the fan wing is in such a way that whenever it rotates, it will actually blow some air in only one particular direction. Okay, so because if you see, this geometry of the blade will be in such a way that even though whenever fluid is moving axially to the shaft, some component of tangential velocity will still exist and it will hit the blades. Okay, so that's how it's very important. Okay, now if you see in this expression, normally in case of radial turbines, if you want to produce maximum head, means if you want to generate maximum power of a turbine, just now I have shown you one thing. Now see here, I will show you this Francis turbine. I have shown you Francis turbine. I have shown you here. I told you one thing, fluid is coming tangentially like this and it is entering radially, correct? Why it is radial? Have you ever understood? So the reason for this being radial is, you will get this formula anyhow, you will see in hydraulic machines and all, this formula will be derived. It's very simple formula basically, which is from this actually. Okay, from this equation only we will again derive there. But normally if you see this is the head supplied by fluid to rotor, correct? This is the energy supplied by the fluid to rotor per unit weight of the fluid. Now this VWT is positive quantity because you have some length, you have some velocity. U2 is also some positive quantity, it has some velocity. Okay, now this is a positive quantity. Now if you want to maximize this quantity, the minimum thing that you can do is making this quantity 0, correct? If you want to maximize this head supplied by the fluid to the water, this VW to U2, this should be made 0. If that should be made 0, this VW2 should be made 0. What is the meaning of that? At the outlet, the flow should not have any tangential velocity, means the flow should be radial. That's why if you see, the flow should be purely radial at the outlet. So that's why if you see in this diagrams and all, the fluid never leaves tangentially, it always enters radially and it falls to the center. Actually it falls downwards. Okay, so that's why in case of reaction turbines, normally in case of Pelton wheel, not Pelton wheel, in case of Francis turbines or reaction turbines, the thing that happens here is fluid enters radially, but fluid enters tangentially but never comes out tangentially. Okay, because here your main job is to make this VW2 value 0, so that the head supplied to the turbine actually increases. So from design point of view, they will actually bend the flow passes to radially. Okay, so that at the exit there is no tangential velocity for the fluid. So whatever the fluid that is coming out, that is no more used for the rotation of the things. Okay, and but again one thing, it can actually do one thing. Many times you see a Francis turbine and a Kaplan turbine are connected to each other. What happens? Look, fluid is entering like this and falling like this, correct, into this pipe, whatever is there. So let us suppose whenever fluid is falling into this pipe, of course energy will be low because already it has impacted the water, so definitely kinetic energy will come down. That's one thing. Second thing, whatever is the small energy that is coming here, look, fluid is coming vertically in this direction. Let us suppose if you keep a axial turbine, means let us suppose if you keep your this fan, whatever is available at that location, then definitely will the fan rotate because there is some high velocity fluid which is coming and hitting the blades. So that's why normally sometimes this shaft is coupled with this Kaplan turbine shaft, so that some excess power can be generated. Okay, normally you might have seen this in normally windmills and all are the Francis case of turbines. You see axially fluid enters the blades and all these things happen. Okay, so but anyhow, if you will find more applications of this when you talk about hydraulic machines. Okay, so there if you want to maximize this VW2 is actually made 0 in this case. Okay, so if you see this VW2 term is basically made 0 in that case, so that the head delivered by the fluid to the water will be very high actually. Okay, so this is the case. So anyhow, so these are the some quite applications of this Okay, so here if you see, I just want to write one thing in this case. Anyhow, if you see the net torque acting on the fluid is equal to net rate of angular momentum across or leaving, you can write leaving the control surface, which can be written as sigma t is equal to m dot relative velocity into r at the outlet, of course vectors if you write, at the outlet minus m dot v r bar into r at the inlet actually. Okay, so this is the case that you come up with. Okay, so this is basically for the angular momentum case that we did. Okay, but you can see momentum, this linear momentum equations, this is the angular momentum equation. Of course, if you see this equation which you have here is basically the angular momentum equation. This equation which I is here, so this is the angular momentum equation. Okay, angular momentum equation, clear? So that's how from this Reynolds transport theorem we can talk about the moment conservation equation, mass equation, linear momentum equation, and the angular momentum equation as well, clear? So that's how we have these things. Okay, so I just want to go quickly to what we have learned today. So I've just erased quickly what we have learned. Then we have taken this RTT. Okay, so we have taken this RTT and then we have explained this Reynolds transport theorem. So basically, system is the amount of matter which you identify in any flow conditions, and control volume is the region in space what you identify. So volume can be moving, can stay constant at any time, whatever can happen. So system can actually move because of the flow. So now if you see, we have done certain mathematical analysis for identifying the mass flow rates, all these things, and we derived finally this equation which is the Reynolds transport equation, and this is the equation. Okay, so now if you see this, we have applied this equation to the mass independently, then to the momentum, and also to the angular momentum case. Okay, so these are the things that we have discussed in today's session. Okay, so we will end this session here and we will see the applications of this, means jet heating vanes, jet heating plates, all these things we will see in the upcoming session, that is at 7 p.m. So is this clear to all of you?